On the night of the 14th of November 2025, an astronomer named Robert Stein was sitting at his computer at NASA's Goddard Space Flight Center in Maryland, running a new artificial intelligence algorithm through data from a telescope in Southern California. The algorithm had one job. Every night, the Zwicky Transient Facility at Palomar Observatory detects roughly 500,000 flashes of light across the sky, supernovae, variable stars, distant explosions, and things that have no immediate explanation. 500,000 per night. The algorithm was trained to find one specific type of event, tonelide that flood, the signature of a star being ripped apart by a black hole. Stein had built this tool specifically to search for tidal disruption events that appeared in the wrong place. Not at the centers of galaxies where every textbook says supermassive black holes live, in the outskirts, in the dark. In places where, by every model we had, a black hole of that size had no business being. He had been running it for months. It kept finding events at galaxy centers, exactly where the textbooks predicted. Then on that November night, it flagged something different. A flare, 750 million light years away, blazing like 10 billion suns. And it was sitting at the very edge of its galaxy, so far from the core that Stein's own words, when he described it this week, were plain and specific. It was very clearly at the edge of where you couldn't even see the galaxy anymore. A black hole in a place where no black hole should be. And before this video is over, you will understand exactly how it got there, because the answer changes something fundamental about what we think galaxies are, what we think black holes do, and how many of these wanderers are out there right now, invisible, moving through the dark between the stars. Before we go any further, if this is the first time you have found this channel, we cover what is actually happening in space right now with the real science and the real people behind it. Hit subscribe. 1 second. You will want to be here for what is coming. To understand what Stein found, you need to understand one fact that has shaped everything astronomers believed about black holes for the last 50 years. Supermassive black holes, the kind that weigh millions or even billions of times more than our sun, are not scattered randomly through galaxies. They sit at the center. Every single one. In our own Milky Way, there is a supermassive black hole called Sagittarius A star, and it sits precisely at the galactic core, 26,000 light years from Earth. In the galaxy Messier 87, the one we photographed directly in 2019, the black hole sits at the center, surrounded by the stars and gas that orbit it. In every galaxy we have studied, in every model we have built, in every simulation we have run, the rule has been the same. The black hole is in the middle. That is where it lives. That is where gravity puts it and keeps it. The reason goes back to how galaxies form. In the early universe, matter collapsed under its own gravity. Gas and dust fell inward. Stars formed. Over hundreds of millions of years, the densest material, including the most massive black holes, sank toward the gravitational center of whatever structure was forming. It is the same reason sediment sinks to the bottom of water, the same reason the sun sits at the center of our solar system. Gravity has a preference. It pulls the heaviest things toward the middle and keeps them there. For decades, this was not a theory astronomers debated. It was a boundary condition, the foundation on which everything else was built. But there was always a problem hiding inside this model, a problem that became harder to ignore the more carefully anyone looked at it. Galaxies are not static. They move, they drift, they collide. And when two galaxies collide, which happens constantly on cosmic timescales, each one brings its own supermassive black hole to the merger, which means the resulting combined galaxy ends up with two supermassive black holes inside it. Not one in the middle, two, and two supermassive black holes in the same galaxy do not simply coexist peacefully. They interact, they pull at each other, they orbit, they spiral closer together over millions of years. And when they finally merge, when two objects each weighing millions of solar masses collide, the violence of that event and the gravitational waves it produces can do something that seems physically impossible. It can kick one of them out. The physics of a gravitational kick were worked out theoretically before anyone had ever seen direct evidence of one. When two black holes merge asymmetrically, when the collision is not perfectly balanced, the gravitational waves produced by the merger are emitted more strongly in one direction than the other, like a rocket exhaust. And by Newton's third law, the newly merged black hole gets pushed in the opposite direction. The force of that kick, in extreme cases, can reach velocities of several thousand kilometers per second. Fast enough, in some scenarios, to send a black hole escaping from its galaxy entirely. In less extreme cases, fast enough to knock a black hole out of the galactic core and send it drifting slowly through the outer regions of the galaxy it once anchored. A wanderer, a black hole with no home galaxy. or a black hole slowly orbiting through the outskirts of a galaxy it can no longer reach the center of. Theorists had been predicting these objects for years. Simulations of galaxy mergers consistently showed that some fraction of black holes should be displaced, pushed off-center, wandering, dark, invisible. But there was a fundamental problem with finding them. A black hole, by definition, emits no light. You cannot see it. You can only see what it does to things around it, the way it bends light, the way it accelerates nearby stars, the glow of gas being heated as it falls in. And a wandering black hole, stripped of the dense stellar environment that surrounds a galactic core, has very little material falling into it. It is not accreting, it is not glowing, it is not doing anything that would make it visible. It is just moving, in the dark, silent. The only way to catch one was to wait for it to do something violent enough to produce a signal. A tidal disruption event, the moment a star drifts too close and gets ripped apart, is the most energetic thing a black hole can do. And a tidal disruption event in the outskirts of a galaxy, far from the center, would be an unmistakable signal of exactly the kind of object theorists had been predicting. The problem was finding one. Tidal disruption events happen, on average, once every 100,000 years per galaxy. They are catastrophic when they occur. But across the billions of galaxies in the observable universe, and with a wide-field telescope scanning 500,000 events per night, the odds of catching one in exactly the wrong place, far from a galactic center, were real. Robert Stein built an algorithm to find it. And on der 14. November 2025, the algorithm did. What Stein's team saw was a flare designated TDE 2025 ABCR. It was in a galaxy 750 million light-years from Earth. A galaxy whose central black hole has a mass of approximately 700 million solar masses, one of the largest black holes we know of. But TDE 2025 ABCR was not at the center of that galaxy. It was 30,000 light-years from the center, in the outskirts, almost invisible against the dark background of intergalactic space. The black hole responsible, the one that ate the star, has a mass of approximately 1 million solar masses. 1 million times the mass of our Sunday, a supermassive black hole by the precise definition, but against the 700 million solar mass black hole at the galaxy's core, it is a fraction. A displaced object that arrived in this outer region through some past event the galaxy no longer shows obvious evidence of. When Stein's team got the initial detection, they moved immediately to confirm it. They pointed the SOAR telescope in Chile at it, the Southern Astrophysical Research Telescope, and obtained an optical spectrum. The spectral features were consistent with a tidal disruption event. Then they turned to NASA's Neil Gehrels Swift Observatory, a space telescope capable of observing ultraviolet and X-ray wavelengths that ground-based instruments cannot reach. Swift's instruments measured the flare's temperature at around 30,000 degrees Celsius and confirmed X-ray emission that placed it firmly in the category of a confirmed tidal disruption event. For several months, the flare was brighter in ultraviolet light than the entire surrounding galaxy. A black hole in the outskirts, invisible and silent for millions of years, had just announced itself by destroying a star, blazing brighter than 10 billion suns for weeks before fading back into the dark. The paper, led by Stein and co-authored by researchers from the University of North Carolina at Chapel Hill, the University of Maryland, NASA Goddard, Penn State, and more than a dozen other institutions, was published on the 27th of July 2026 in the Astrophysical Journal Letters. Jonathan Carney, co-author and PhD student at UNC Chapel Hill, put it plainly. Almost every tidal disruption event ever observed occurred at the center of a galaxy, right where the biggest black holes are expected to be. This one happened tens of thousands of light-years from the center, revealing a massive black hole in a place where nobody would normally look. Here is the part that is not in the headline. When Stein's team examined deep images of the location where the flare occurred, they found no star cluster, no small galaxy, no concentration of stars suggesting this black hole arrived with company. Whatever group of stars once surrounded it has been almost entirely pulled apart by the gravitational influence of the much larger galaxy it is now drifting through. The ratio of the black hole's mass to any remaining stellar mass around it is extreme, far higher than what we normally observe for black holes embedded in stellar populations. This is the signature of a wandering black hole brought in during a past galaxy merger that has been slowly sinking toward the galactic center ever since, losing its surrounding stars along the way. Somewhere in the history of this galaxy, at a time we cannot pinpoint, from a merger whose debris has since been absorbed and erased, two galaxies collided. The smaller one brought its central black hole. The larger galaxy swallowed the smaller one whole. But the black hole survived. Too massive to be fully absorbed, too small to reach the center on its own, It has been drifting through the outer regions of a galaxy that no longer remembers the one it came from. The only reason we know it exists is that a star drifted too close. Now, consider what that means at scale. For years, the standard filter for finding tidal disruption events was simple. Look for a bright flare at the nucleus of a galaxy. That is where the black holes are. Any event that was not at the nuclear center was treated as something else, a supernova, an artifact, a misclassification. The standard pipelines were built on the assumption that the center is where you look. Stein's algorithm broke that assumption deliberately. It was designed specifically to flag events that did not occur at galaxy centers. And TDE 2025 ABCR was not the first candidate it flagged. It was the first one that survived every layer of confirmation. Now that the technique is validated, the search can scale. The Vera Rubin Observatory in Chile, which began full science operations in 2025 and surveys the entire southern sky on a 2-day cadence, is expected to push the annual tidal disruption event discovery rate from tens per year to potentially thousands. With an algorithm capable of identifying off-nuclear events inside that data volume, the number of wandering black holes we can confirm is about to rise dramatically. There is a larger truth here that the paper itself does not state, but that the data implies. The standard model of galaxy evolution assumes that when galaxies merge, their black holes eventually merge too. That the two objects find each other, spiral together, collide, and produce a new unified black hole at the center of the resulting galaxy. This is the model behind our predictions of gravitational wave backgrounds, the low-frequency hum of spacetime that pulsar timing arrays have been trying to detect for years. But if a significant fraction of black holes escape the merger, if some get kicked or stall in the outer regions, or simply never reach each other, then the merger rate is different from what we calculated. The number of binary black hole pairs spiraling toward each other in the cores of galaxies is different. The gravitational wave background is different. Every wandering black hole confirmed is a data point in a calculation we have never been able to make accurately. How often do galaxy mergers produce true coalescences? How often do they produce exiles instead? TDE 2025 is one data point. A single star destroyed 750 million light-years away by a black hole that has been drifting through the dark for longer than the Earth has existed, but the method that found it is now confirmed. And in the era of Vera Rubin, what was a single data point is about to become a census. The black holes we assumed were in the middle, some of them are not. They are drifting. They have been drifting for millions of years. Silent, invisible, waiting for a star to come close enough to finally reveal them. We just built the instrument to listen. Next on this channel, a wildfire burned through NASA's ground station in Spain 4 days ago. The one that talks to Voyager. The one that needs 6 antennas pointed at a single spacecraft just to receive its signal. We have the full story of what the fire actually damaged, what it means for every mission NASA is currently running, and why this happened at the worst possible moment for the Deep Space Network. Subscribe now. That one goes up next.